All right, guys. A very good evening to all of you. Am I audible? Is my voice loud and clear?
Yes, it's loud and clear.
All right, great. Oh, we have two Sirishas. Great. All right, guys, let's get started. Let me know once you guys are able to see the screen as well. Is the screen visible, guys? All right, great. Okay, so yesterday we were discussing about the unsupervised machine learning techniques, out of which we started off with clustering, and we discussed about unsupervised techniques. The first technique was hierarchical clustering. Okay, so we look at the Mumbai's Dabbawala's example to understand clustering, and then we looked at a few examples to understand how that clustering works, and finally, how do we summarize the entire process using a dendrogram. We also talked about k-means clustering yesterday. So yeah, so just to reiterate what we looked at yesterday. So just to speed it up. So we looked at the steps to run k-means algorithm, which is also a clustering technique. So we randomly divide the data set into k clusters, okay, non-overlapping clusters. So k, the criteria is that k should be minimum 2, okay, or greater than equal to 2. So we took for k equal to 3, and we partitioned the data set into 3 non-overlapping random partitions, okay. So this partition is done randomly. So if you run k-means algorithms once again, you will not get the same partitions. You might get different partitions, okay. So then we determine the centroids for all the different clusters, k number of clusters. So if we have k equal to 3, so we have 3 clusters over here, and then we determine the centroids for all the respective clusters. Then we find the distance between each data point to the all the 3 clusters. And then if the data point is not belonging to the same cluster to whose centroid it is closest to, okay. If it is already closest to, let's say, C1 C1 centroid, okay, of cluster C1, then we need not move the data point. But if the distance of the data point to the other cluster is closer, okay, so let's say if it is closer to C2 than C1, then ideally we should move the data point from C1 cluster to C2 cluster. Now, since we are doing movement of data points, right, the data points at earlier stage, okay, let us say we had 30 data points in C1, 40 data points in C2. Now, because of the movement, right, there will be subtraction of data point from one cluster and addition of data point to another cluster. Now, since the centroid calculation involves all the respective data points in that particular cluster, right? So that is the reason we need to recompute the cluster centroids. So once the data point has been moved, okay, so we need to recompute the cluster centroids, and then we keep on doing this same steps iteratively, okay, until there are no more movements that are possible, okay. So basically all the data points are closer to their respective cluster centroids. So that is the goal over here. All right, okay. Now or the different platforms, okay, there are there, you can also Google for the code for the same, okay. But the only thing is, okay, due to time constraint, we are not able to show it over here, okay, in this particular 10-hour session, right? So usually we have a full length data science course, full-fledged data science course, wherein we can go through all into more details, okay, step by step, along with the program as well. But here, due to time constraints, we won't be able to, cover all that stuff. Ideally, we should have been starting with supervised machine learning today, but I'm just covering up what we left yesterday, and then we'll jump to supervised machine learning today as well. Okay. All right. Great. All right. Now, at the end of the algorithm, right? So we said that the expected behavior is that all the data points will be clinged, okay, or remain closest within that particular cluster. So the within cluster variability, okay, so something called as within cluster variability. I'll just write it over here. So here there is something called as within cluster variability. So we already understood what is variability, variance, and stuff like that on the first day, right? So when we say within cluster variability, whether data points are too much dispersed, okay, or there is less variance, which means that all the data points are clinged or very much attached to the cluster centroid. Is that what we are talking about? If all the data points are clinged or attached to the cluster centroid, which means that the within cluster variance is very low, okay, and the k that we have chosen is good enough for this kind of a problem or this kind of a data set that we are working with. But let us say if the within cluster variability is high, so in which case it will be high, guys? Example of, I give you three fruits, grapes, apples, and bananas into one single basket. Okay, so I give you one single basket, grapes, bananas, and apples, all of them. Okay, and I ask them, okay, I ask you to segregate. So basically separate them based on their color, taste, structure, whatever it is, right? Based on any kind of feature, I ask you to separate this out. So what you will do, you will again go ahead, I'll give you two baskets. Okay, I'll give you two baskets. So basically I'm saying k equal to 2. But ideally we have three types of fruits, okay, but I'm giving you only two baskets. So what will happen? All the apples and bananas might get segregated or separated, but the grapes will have to be distributed in both the baskets because it does not have a separate basket for itself. So similarly, if there is a different type of data points, if there are different type of data points within this cluster, right, they will not move closer to this particular cluster centroid, right? So the within cluster variance will be high. So when the within cluster variance is high, it denotes that we should, get one more basket for grapes as well. Like with this example that I'm just giving an analogy, right? Grapes, bananas, and apples into one basket. So in order to separate all of these three clearly, right, we need three baskets. So similarly, when the within cluster variance is high, we need to increase the value of k. We need to increase the value of k so that these data points which are not able to get cling together, okay, so basically they are not able to cling to this cluster centroid or this cluster centroid or this cluster centroid, which means that they need a separate cluster of themselves so that they can be clearly separated from the rest of the data points. Okay, so which means that depending upon the within cluster variability, we need to choose a optimal value of k. Very difficult to understand, okay, how or what should be the optimal value of k that should be chosen so that you can effectively run this k-means algorithm. Okay, so for that we have a technique called as elbow method or the scree plot. Okay, so that we're going to discuss next. So I'm just going to run you through this. But before we discuss about the scree plot, let's take a similar example that we took yesterday for hierarchical clustering, right? So we had a data set like this. Okay, so what we can do, we can think of this as a data set, okay, wherein these are your variable 1, variable 2. Basically you can call them as feature 1, feature 2 as well. Okay, and now what I'm going to do, I'm going to have 1, 2, 3, 4, and 5 data points. So I'm going to plot them into a scatter plot. Now when you look at the scatter plot, okay, what we're going to do is we are going to, if you just visually look at this, right, if you visually just look at this, these two data points seem to be closer to together, and we can form one cluster, and we can club these three because by visually looking at it, these look to be closer to each other, and that is how we can form these clusters. But let us purposefully do what? Let us purposefully put 3 into the cluster with 1 and 2. Let us purposefully create a cluster of 1, 2, and 3, and we'll create a cluster of 4 and 5. Okay, so we start with clusters A, which is 1, 2, and 3, and cluster B, which is comprising of 4. So this is your cluster A, and this is your cluster B. Okay, now what we're going to do is, so Khushi, for how features are selected? So these features are selected with the help of domain experts. So the domain experts will tell us which features to select, which are important for solving that particular business problem. Okay. So based on what kind of business problem you're solving, like if I want to issue a loan to a customer, what are the important factors I should look at, or which are the important variables I should look at? So to carefully select those variables or features, we need to take the help of domain experts, like all the banking subject matter experts who can tell us, okay, we should look at the CIBIL score, what is the repayment capability, what are the existing loans that the guy is already repaying, right? What is his salary? If he takes a new loan, whether he will be able to repay that, or whether he will end up, defaulting on that loan. So all these kind of all this kind of analysis, right, is required to be done by the subject matter experts, and the subject matter experts will tell us, okay, take these features and you should focus on these. Okay, so that is what something feature engineering that comes under feature engineering. Okay, and for feature engineering, we need to take the help of domain experts to carefully craft the features. Okay, all right, Kush. Okay, so let's start with this particular example for k-means. So I'm going to create two clusters, okay, random two clusters A and B, which comprises of first data point and this fourth and fifth. Okay, now if you go and look at this particular slide, okay, so keep this slide in mind when we are discussing. So first we determine the value of k. So we have k equal to 2 now. Okay, now we have divided the data set into two parts, non-overlapping parts. Now determine, the third point is determine the cluster centroids, right? So we need to figure out the centroids. So let us go ahead, find the centroids for these two clusters. How do we find the centroids for these two clusters? So this particular data point will have certain x1, y1. C and YC, basically the x and y coordinates of the centroid. In order to compute the centroid, XC is computed as your x1 plus x2 plus x3 divided by 3. Your YC is calculated as y1 plus y2 plus y3 divided by 3, since we have three data points over here. Okay, so that is how we determine the coordinates of the centroid x and y. So let us find out this. Okay, so in order to find the centroids, so this is your x1 y1, this is your x2 y2, right, and this is your x3 y3. So to get the xc, I'll have to add up all these three. So this is nothing but 6 plus 1 7, so 7 divided by 3, and your yc will be nothing but your 5 6 and 7. Again, this will be 7 divided by 3. So the centroid location, okay, for A will be nothing but 2.3 and 2.3. Right, so that is how I determined the central location for A. Now for B as well, okay, for B as well, we have to sum of these and divide by 2. So this is 12 by 2, which is all right. Clear up, clear, everyone. We have figured out the centroid locations for both the clusters A and B. Now what is the next step? The next step is take all the data points, first, second, third, fourth, and fifth data point. Okay. Now, if you look at the first data point and its coordinates, what are the coordinates of the first data point? So the first data point ke coordinates were the first data points coordinates were 1 and 1. Okay, so x1 y1 is nothing but 1 1. Now what we need to do is we need to take this centroid. Okay, so the centroid is 2.33 for cluster A, comma 2.33. Okay, so these are the centroid locations, and for this the centroid location is 6 comma 7. Now I need to apply Euclidean distance method in order to find the distance between. Okay, so if you remember, this was your first data point, you had the second data point over here, the third data point was somewhere over here. Okay, and the centroid location, okay, so the centroid location is over here. I need to find the distance from first data point to the centroid, second data point to the centroid, and third data point to the centroid. Okay, so this is for cluster A. Similarly, I need to find the distance of the same data point from cluster A. Okay, and there was this fourth and fifth data point. Okay, this was a part of cluster B. I need to also find the centroid location of this particular cluster. Then find the distance of 1 to this A cluster centroid and distance from 1 to the B centroid cluster. So this is what we're doing over here. So this is what we're going to do. So 1, 1. Item 1 was 1, 1. So I'm going to apply the Euclidean distance. So what does Euclidean distance method say? Root of x1. So this is x2 minus x1 whole square plus y2 minus y1 whole square. So this is how we find the Euclidean distance by computing this formula. Okay. So we're going to use the same formula. So 1 minus 2.33 whole squared plus 1 minus 2 points. So this is again the second coordinate minus 2.33 whole square. And this entire bracket, we are going to put it into square root. So the distance of first data point to the cluster centroid A is 1.89. Similarly, I calculated the distance of first data point to cluster centroid B, okay, which is 7.81. So as you can see, the minimal distance is 1.89. And this data point, first data point, is already a part of cluster A itself. So we did not make any movement, okay? Because the closest distance is towards the centroid of A only. And B ka centroid say first data point is too far away, which is 7.81, right? So what we can conclude that the first data point need not be moved. We can keep it in cluster A itself. Then we go to the second data point, find the distance, okay, similarly, which is 1.37 and 7.21. Again, we find that second data point is also closer to the cluster A centroid and it should remain as a part of cluster A centroid only. We need not do any movement. So for both these data points, first and second, as you can see, those are very much closer to the cluster A centroid and we will not make any movement. Now let's go to the third data point. In the third data point, as you can see, 4, 5 are the coordinates, I mean, of the data point, third. Now I subtract from the cluster centroid of A coordinates and take a square root. Okay, calculate the distance. So this distance comes to be 3.14 and the distance of third data point to 2.83. Now here is the problem. Okay, what is the problem? This data point, item third, okay, is distance to the okay, am I audible, guys? Am I audible now? Khushi? Chandrika? All right. All right, guys, let's continue. Okay, is the screen visible, guys? No, audio is working, Khushi. I was not speaking. Okay. Monica, can you hear us now? As well as see the screen? Okay, great. Thanks for confirming, guys. Thank you. All right. So what we were talking about is we were talking about this third data point. Okay. Remember what we did? We had purposefully taken data point 3 into cluster A. Though we can visually see that it should be closer to centroid B. Okay. So it should be a part of B. But we purposefully took it in A so that we can prove that this data point, okay, is more closer to cluster B centroid rather than the cluster A centroid. And that is the reason we need to move this data point from cluster A to cluster B. Okay. So just to exemplify or showcase you that particular thing, we have purposefully added it to the cluster A. And this is, as you can evidently see, that this particular distance 2.83 is very much closer, I mean, very much minimal as compared to cluster A centroid distance, right? So that is the reason we need to move this data point from A to B, and that is what we are doing over here. Okay. Now, after, since we are removing one data point, okay, since we are removing one data point from the cluster. So remember, we had 3 data points in cluster A, we had 2 data points in cluster B. Okay. So what we are doing, we are moving this third data point from cluster A to B, which means that now I'll have only 2 data points in cluster A, whereas there will be addition of data point into cluster B. And that is the reason we need to recompute the cluster centroids now. Okay. So we are going to recompute the cluster centroids. Now in cluster A, there will be only 2 data points, 1 and 2, whereas in cluster B, there will be only 3, 4, and 5. Okay. So this is, so what we need to do, we need to again recompute this cluster centroids of cluster B and cluster A. Okay. So after recomputing, we can see that the new cluster centroids. Okay. So now 1 and 2 are into one cluster, and 3, 4, and 5 are into the another cluster. Okay. And these are the new centroids that we are going to find out for these two clusters A and B now. So centroid A is having 1.5, 1 as the new centroid coordinates, and the centroid B, I mean, cluster B centroid is having new coordinates, which is 5.33 and 6.33. Remember, earlier this was 6 and 7, and earlier this was 2.33, 2.33, right? So due to the movement of the data point from cluster A to cluster B, now we had to recompute the cluster centroid, which is now 1.5, 1 and 5.3 and 6.33. Now we again redo the entire process. Okay. So what we do? We again redo the entire process. Okay. And we see that item A, or the first data point, okay, is having 0.5 distance to cluster A centroid and 6.87 distance to cluster B centroid. So we can see that it is already a part of A. It should remain a part of A. There is no need to move this data point. Similarly, for the second data point, it is closer to cluster centroid A. We keep it, we retain it in cluster A itself. There is no need to move it to cluster B. Now the third data point, remember, we have moved it already to cluster C, cluster B now. Okay. So we calculate the distance 1.89. Okay. And this is 4.72. And now we can see that clearly it is closer to cluster centroid B. Okay. And it is also part of cluster centroid B. So we need not make the movement. Similarly, we do for fourth data point, fifth data point, and find that fourth and fifth are already a part of cluster B, where they should belong to. And now we can see that there is no movement possible. All the data points are closer to their respective cluster centroids. So there is no need to make any movement here. Okay. And that is the reason we stop the algorithm over here. And that is how the algorithm stops. And so this is what is the end result. Okay. That you can see, we have two different separate clusters. Okay. Now coming to the, so we will not discuss this example because we are short on time, but let us discuss, okay, how to select the optimal value of K. Okay. How do we determine what should be the value of K so that we can effectively run this algorithm on the data set and get the required clusters? Okay. So for that, all right, we will go with something called as the elbow graph, or also called as the scree plot. This is also called as the scree plot. Okay. So what is this scree plot all about? On the y-axis, we are going to plot the within cluster variability. Okay. And on the x-axis, we are going to plot the values of K. So for K equal to 1, obviously this is not valid. We will have the highest variability because all the data points will be mixed with each other. Okay. But as you go on making 2 partitions, 3 partitions, 4 partitions, remember that grapes, apples, and bananas wala example, which I, helped you to understand. So if I mix 3 fruits and I just give you 2 baskets, you won't be able to segregate or separate all the 3 different fruits into different, I mean, clearly there will be no clear differentiation. So the within cluster variability will be a little bit high because there are dissimilar items being grouped together. Okay. So if I give you 2 baskets, in one basket you can put apples, in the other basket you can put bananas. But what about grapes? There is no separate basket for grapes to be put in, right? So some grapes will be over here, some grapes will be over here, and thereby they will increase the within cluster variability. Okay. So initially, when all grapes, bananas, and apples are together, the within cluster variability will be very, very high. So that is where when your K is equal to 1. So everything is together in one basket. But as you get 2 baskets, you can segregate them. So you can move the apples together into other basket, bananas into together other basket, but still grapes are remaining, right? Which means that they need another separate basket. So what will happen to the within cluster variability if I increase the K? It will further drop down. So likewise, but now if I give you 4 baskets, okay, and I say that now you have three fruits, grapes, apples, and banana, and you can separate them. You'll just separate all of them into 3 baskets only. So there is no use of the 4th basket. The 4th basket is of no use. Okay. Even if I give the 5th basket, it will be of no use. Even if I give the 6th basket, there will be of no use. Why? Because you already segregated the required number of fruits into the 3 baskets, right? So if you go by this analogy, right, even if I keep on increasing the value of K, after a certain point, the within cluster variability will not fall down. Why? Because there is no point. You have already segregated all the required fruits into the different baskets, right? So the within cluster variability will not fall further down, and this shape of the graph will become something like this. So this shape, if you look at your arm, right, this point is your elbow. If you check your hand, okay, and at the corner of your hand, right? So if you pull your hand towards your shoulder, you'll see that there will be a corner point getting formed. This is the elbow point. So that elbow is where your optimal value of K exists. So wherever this K value, so here in this case, let us say K equal to 3. So here K equal to 3 is the optimal value. So wherever you get the elbow of your scree plot or your elbow graph, right? And that is the reason we call this as the elbow graph itself. Okay. Why? Because it depicts at which point the within cluster variability has stopped reducing or does not reduce too drastically. Whereas if you see at 1 and 2, right, it has fallen down drastically. But from the point where it does not decrease drastically, that is the optimal point, or that is the optimal value of K that you should choose for your algorithm to run. Are you guys with me? How to choose the value of K, optimal value of K? Are you guys with me so far? Is the concept clear now? All right. Great, guys. Great. So basically, you can use K-means algorithm for larger data sets when you have 1,100 records or something like that, right? You can go with K-means, okay? And if you have smaller data set, let's say 100 or 1,000 to 5,000 records, right? So in that case, you can go with something called as hierarchical clustering, okay? So hierarchical clustering is majorly useful when you have smaller data sets. And if you have larger data sets, you can go with your K-means algorithm. All right, guys, any questions, queries so far? Is it making sense? All right, great. So we will stop here on the unsupervised machine learning part, guys. Okay. And now we will move on to our supervised machine learning, which is our day 3. Okay. Okay, so now we are going to discuss about the supervised machine learning. Does anyone remember what was the difference between supervised machine learning and unsupervised machine learning? We discussed yesterday. Does anyone remember what is the difference between the two? I gave you a very clear difference. Where the y variable is present. Yes, here. Rohit, we didn't discuss that yet. So due to time limitations, we won't be able to discuss DB scan. But yes, I have given you 2 majorly used algorithms and understanding of the both, Rohit. So Omkar is saying X and Y variables in supervised. That's correct. So Suresh was saying under the supervision. Okay, so Y variable is under supervision, Suresh Babu, in supervised learning. Okay, whereas there is no Y variable in unsupervised. Okay, and that is the reason it is called as unsupervised machine learning. So data set contains only Y, then it is. So Sakshi, it is the other way around. So if the data set contains only y, okay, only y, then that data set is of no use to you, right? What will you do with the only y, right? You need the input as well. Output, सिर्फ output लेके क्या करोगे? So when your data set contains only x variables, not y, only x variables, only input variables, there is no target variable. Okay. Oh yeah. So it was a typo. Great, great. Rohit is saying we predict y variable in supervised machine learning. Yes, that's correct. Very good, guys. You remember the difference between supervised and unsupervised. So that's good to know. All right, let's proceed then with supervised machine learning. So until now, we were discussing about the unsupervised machine learning techniques. Okay, how we can make sense of the data wherein we don't have any target, specific target variable. Okay, but now in supervised machine learning, okay, we are going to look at regression and classification problems. So I'll let you know what is the regression problem and what is the classification problem. Okay, but as of today, okay, I mean for today we are going to look at the regression techniques, and out of the regression techniques, we are going to first look at the simple linear regression. Okay, so we're going to look at what is regression, why do we go for regression techniques. Okay, how do we start looking at linear regression, right? So first, to understand the relationship between any two variables, first we have to look at the scatter plot, right? Then we look at the measures of association. So basically, how can we quantify the level of association between two variables? So we already talked about correlation coefficient yesterday, right? Then we'll see how we can use all these concepts together and perform simple linear regression. Okay, simple linear. Then once we are able to understand simple linear regression, then we will go for multiple linear regression. All right. So we'll talk about all these things in today's session. Okay. Now, when we talk about a regression analysis, what is regression analysis all about? So regression analysis combined with a correlation. Okay. Now, you guys yesterday, I think yesterday or day before yesterday, we already discussed about the correlation coefficient. Okay. So what kind of correlations we exist, guys? If I have to talk about linearly associated variables, right? So we looked at two different kinds of correlations. Do you remember which were they? Yes, Rohit, positive and negative. Yes, that's correct. So when do we say it's a positive correlation, Rohit? When both the variables travel in opposite direction, right? Okay, so when x increases, y increases. That's right, Rohit. So when both the variables travel together in the same direction, either they both increase together or they both decrease together. Yes, Sakshi, you're right. Yes, Omkar, Kushi, yes, you guys are correct. So basically, when both the variables increase together, so let us say if we have V1 and V2, if both increase together or both decrease together, right? In that case, we say they are positively correlated. And when both move in opposite directions, we call it as a negative correlation. So you guys remember what the correlation concept is, okay? So we are going to combine this correlation analysis along with the regression analysis. Now, what is this regression analysis? Okay. Now, by combining this regression analysis with correlation, we would be able to predict the future performance, okay, of any business metric based on the past data. So in every business we have the past data, and as you guys rightly told me what was the definition of data science, right? We should be able to generate actionable insights, right? So in order to generate actionable insights, right, or in order to predict any particular variable of interest, right, what we need to do? We need to analyze the past data, right? So based on the past data, we are going to do regression analysis combined with correlation. Okay. Sorry. So using both of this, we are going to predict the future performance, or we can predict, or we can build a model and we can predict what would be the value of that particular variable of interest or target variable or output variable or any business metric which is of our interest. Okay. So let us break down all these things together and then combine them together to understand what is linear regression. Okay. So while correlation explains the degree of a linear relationship that exists between two variables, okay, whereas regression defines the relationship more precisely. So what do you mean by regression? It defines the relation more precisely in the sense that, okay, you can generate an equation. You can generate an equation such that, now what is that equation? So I'll give certain input. I'll give certain input to a box. Okay. And I'll say that, hey, predict me the output. Give me the output. Okay. So for that, first we need to establish a relationship between the input and the output. Okay. So basically between your X variables and the Y variables. And this relationship we need to model using a algorithm. And this particular model is nothing but what we are talking about as a part of this particular regression analysis. So regression analysis is a tool that uses data on relevant variables to develop a prediction equation or a model. Okay, so our goal is to develop a prediction equation or a model such that given certain input with regards to the X variable, we are able to successfully predict or generate the output. Okay, now it generates that an equation. So basically this model or equation that we were talking about, okay, to describe the statistical relationship. Now, first we need to understand how is a statistical relationship different from the other relationships, right? So what is a statistical relationship? Let us try to understand that. So, sorry. So simple linear regression is useful for finding a relationship between two continuous variables. Okay. So one is called as the predictor or the independent variable or the X variable, or you can also call it as the input variable. And the other is your response variable or dependent variable. You can also simply call it as a Y variable. Okay. So our goal is to establish a relationship between these two variables, okay, X and Y. Now this relationship that we want to build or uncover is nothing but we need to look for the statistical relationship and not the deterministic relationship. Now, what is a deterministic relationship? Okay, let us understand. How much is 1 kilometer, guys? How many meters? Basic question. Correct, Rohit. It is 1000 meters, right? So whatever you do, wherever you go on earth, this particular relationship does not change. So this is a deterministic relationship. Okay, 1 kilometer, or you can say 1 kg is equal to 1000 grams, right? So this is kind of a deterministic relationship. We are not looking for a deterministic relationship, but we are trying to look for a statistical relationship. Now, what do we mean by statistical relationship? Let us look at that. So if we want to find the relationship between weight and height, okay, so that would be something as called as a statistical relationship. We would be interested to find out how these two variables are statistically related to each other. How? We are interested in finding out that. And for that, okay, we need to conduct the regression plus correlation analysis. Okay, so we need to do this so that we can develop the model. So far with me, guys, what is the goal over here? Our goal here is to develop an regression equation or a model or an algorithm, whatever you call it. Okay, so such that it should be able to establish the statistical relationship between your input variable X and output variable Y. Simple, in simple terms. Yeah, Kushi, I will just explain it again. Is it clear? Are we able to follow, guys? Our goal is to find or describe the statistical relationship between the input variable and output variable in the form of a regression equation or a model or algorithm, whatever you call it. Okay. Okay, guys. So simple linear regression is useful to find the relationship, and that too, we are interested in finding the statistical relationship between any two variables such that we should be able to model the relationship between those input and output variable. Okay, so let us find out using an example. Okay, maybe this is all theoretical, right? Let us take an actual example. Now let us say that you guys, after completing your education, right, probably most of you are into engineering colleges or in your last year of education, right? So what is your next goal? Your goal is to find a job, or you can apply for multiple jobs. Now, what you would do is you'll create a resume, you'll float it with all the consultant companies, right? So usually you can directly either take your resume and send it to the XYZ company or ABC company, right? You can send them directly to their HRs and they will screen your resume and they will call you for interview. Or what you can do, you can send the resume to a consultancy as well. Now, what are these consultancy companies doing? These consultancy companies, they get requirements from multiple companies, okay, that we are looking for so and so person with these skill set. Okay, let us say data science skill set. Okay, and what this consultancy will do, it will also collect resumes, okay, from multiple people like you. Like take, for example, take Naukri.com, right? Or timesjobs.com. These are all nothing but different consultancies. So what they do, they have the requirements, they have the resume of people who have the required skill sets. Now their job is to match the resume and the requirements so that they can place the candidates in the required role. Okay. Now, what the consultancy does is it is having data of, let us say, all people who applied so far with X number of experiences, let us say. Okay. And let us say what were their salaries. Okay. They got. So X is nothing but your experiences. Okay. Let us say Y is nothing but the salary. Now tell me guys, is a salary dependent on years of experience or years of experiences depend upon the salary you get? So Rohit is saying salary is dependent on years of experience that you carry. Correct. So tell me now, salary depends on years of experience, right? So who is dependent on who? So salary is dependent on years of experience. So who is the dependent variable here and who is the independent variable here? Can you guys guess? Which variable is independent and which variable is dependent? Salary is dependent on experience. So your experience becomes your input variable or the X variable. Okay. And your salary becomes your Y variable, which is dependent upon X to derive its own value. As you guys told me, right? The salary is dependent on years of experience you have, right? So salary derives its own value based on the years of experience. So let us say whatever the consultancy till date, has placed different people, right? So it has recorded all the data. It has figured out that, okay, for 0 years of experience, what is the average salary that is offered? So let us say average salary offered is 25K per month. Okay. Then for 2 years of experience, let us say what is the salary offered? Let us say 50K per month. For 3 years of salary, 3 years of experience, let us say 60K is the salary. Okay. So the consultancy can definitely keep a track of all this data. What were the number of people placed? What salaries they got? What was their years of experience based on, which they got this particular salary? Yes or no? Can the consultancy maintain that data, that kind of a data? They can, right? They should be, they might be, or they should be maintaining this kind of data. Do you guys agree with me? Now, let us say I directly have for 5 years, which is like 80K. Okay. And now tomorrow I get a person, okay, who is having 4 years of experience. Now in this table, we don't have a salary for 4 years of experience. Okay. There is a person who comes with 4 years of experience. Now, can we predict what salary he might expect in the industry? Is it possible to figure out what might be the salary he can expect? Correct, Gangotri, between 60 to 80. But if I want to figure out or predict the precise salary, Krushi, it is very easy, right? 70K. Remember, we are trying to find the statistical relationship, not the deterministic relationship. Okay. Now, since the what you can say, the salaries are in an incremental order, I just you are able to say 70K. Okay. But if you want to find out, okay, as close to actual possible, if I want to do the prediction of as close to actual, right, I need to establish a relationship between these two variables, experience and salary. Okay. And this relationship should be nothing but your statistical relationship. And let us see how we can do this. Okay. Now tell me guys, how can I find out the relationship between any two variables? You guys have already learned it. in this last 2 to 3 days of session. How can I find out whether two variables are related to each other or not? Which numerical or graphical technique we can apply? उसके भी पहले क्या करेंगे गंगोत्री and Rohit? Even before you do what you are saying, right? What is a simple technique to find out whether they are related to each other or not? What kind of a plot will you plot? Nah, Rohit, you're going too ahead. Yes, Gangotri. Scattered plot, right? Bang on. Remember, we looked at all the different graphical techniques. Scatter plot is a plot used to determine whether there is a certain relationship. Okay, are they linearly associated with each other or not, right? So for that, can I plot a scatter plot with this kind of a data? Can I put this on X and Y axis like this? Can I put this on X and Y axis like this? Like I can put X on this, Y on this. So X is what? X is nothing but years of experience. Can I put salary on this particular Y axis? Okay. So for the first data point, for 0, 25. So for 0 years of experience, 25. This is the first point. Then we can have 1 year of experience, 2 years of experience. So for 2 years of experience, 50K. So 50K. So this is 25K. So this is 50K. So this is somewhere over here. Yahan pe aayega wo data point. Can I plot like this? Scatter plot, guys. Simple. I can plot, right? There's no harm in plotting that. Yes or no? Yes. So let us do that. So this is the sample data that we have, the years of experience, and this is the salary that we are having. And as you guys told me, right, the salary is dependent on years of experience. So here, this is my target variable or Y variable that I'm interested to predict. And this is the input variable, years of experience. And say tomorrow there is a person coming with 5 years of experience. Now there is no 5 in this entire thing. Okay. So if I want to predict what would be the probable salary that this guy with 5 years of experience can expect, right? So what can I do? I need to find out the relationship between experience and salary, those two variables, right? Simple thing. How can we do it? You guys told me you can go with a scatter plot, right? So let us go with a scatter plot. So can I plot this data like this? What do you see, guys? If I plot a scatter plot out of the data that we have, I'm getting something like this. What do you infer from this plot? What is the inference that you can draw from this plot? So Rohit is saying it's a positive correlation. Yes, Gangotri, that is correct. Positive correlation. Can I draw a line passing through this data points? Who can represent these data points? Can I draw a line passing through these data points, which can be a representative of the data points, right? So Kushi is saying yes, but not that straight. Okay, Rohit, why can't I draw? I can draw a line like this, right, guys? I can draw a line like this. Let us say I can also draw a line like this, right? I can also draw a line, let us say like this, right? Okay. So how many lines can I draw, guys, which can represent those points? Tell me. I can draw a line like this. Oh, but you guys didn't specify me how to draw the line, right? So I'm just drawing as per my wish. So practically, how many lines can I draw, guys, to represent those data points? So Kushi is saying infinite number of infinite number of lines. So Rohit is also saying infinite number of lines. Do you guys agree, all of you? Others? You have close to 200 participants watching this session. Do you guys agree? So we can draw infinite number of lines, right? That's good, Rohit. According to the person's skill, it depends which kind of a line, right? But how do I figure out which is the best line out of all of these? How do I figure out which is the best line? Which is the best representative? Many, but best fit line we should choose, Lakshmi Devi. Okay. Gangadhar is saying we should draw the line which covers more points. Okay. Giridhar is saying the line closest to all data points. Okay. To cover maximum dots. That's right, Suresh Babu. The line which covers majority. Majority. Good, good, good. Okay, so let us do this. How do we figure out the best fit line? So whatever you guys are saying is correct, but mathematically, how can I figure out how to choose the best fit line? Equidistant from all data points. Omkar, is it really possible to draw a line which is equidistant from all the data points? Is it practically possible? Hmm. You can draw a line which is as close as possible to maximum number of data points. You can't satisfy every data point, right? You can't say I can draw a line which will be passing through all the data points. Then I have to draw a zigzag line then, right? A non-linear line I have to draw then in that case, right? But let us say if I have to choose to keep things simple, right? Let us say which should be the best fit line, right? Or which line we should go with. So in order to choose the best fit line, we need to understand something called as the error. We need to first understand something called as error. Now, what is the error? Okay. Okay, for line, right? These are all lines. Now, what is the equation of line, guys? How do we represent a line? What is the equation of line? Yeah, equation of line. Since we are talking about line over here, any line. Yes, y is equal to mx plus c. That's correct. So if this is your line, right? How do I find out the line? Equation y is equal to mx plus c. Now, if I go by your logic, y is equal to mx plus c. What is y? What is m? What is x? What is c? Right? You guys need to tell me. Yes, Chandrika, Omkar, Khushi. What is m? What is m, guys? Okay, y and x are nothing but the coordinate system. Okay, that's fine. What about m and c? What are m and c then? So she's saying m is the slope. Okay, slope. How do we define slope? How do we calculate the slope of a line? Any idea? High school geometry, high school maths. How do we find the slope? So Lakshmi Devi is saying c is intercept. Okay, so c is your intercept. But which intercept, Lakshmi? X or y? Okay, y intercept. Good. Slope at the rate y divided by at the rate x. Now, what is that, Rohit? How do we calculate the slope? Yes, Giridhar y2 minus y1 divided by x2 minus x1. Yes. So we find slope by using this formula y2 minus y1 divided by x2 minus x1. Now, what are these x2 and y1? You can choose any 2 points on the line. So let us say if I choose this point, if I choose this point. So this point will have certain x1, y1. This point will have certain x2, y2. So you can choose any 2 points on the line, okay, and figure out what is the slope of this particular line. How? You can subtract the y coordinates divided by the subtraction of x coordinates. So that is how your slope is defined. Okay, so that will give you the idea of slope. Very good. What about the y-intercept? Yes, so wherever the line intersects the y-axis, so that is your c. Okay, now the same equation, guys. Okay, the same equation. Now I'm going to just rephrase. I'm just going to just rephrase that y is equal to mx plus c. Okay, y is equal to mx plus c. Okay, I'm just going to rephrase this as y cap. Y cap is nothing but the predicted value of y is equal to, okay. Now I'm just going to represent this as x is x, okay. Now instead of the slope m, I'm going to use something called as beta 1, okay, plus, okay, this is nothing but your c. Instead of c, I'm just going to put beta naught, okay. So again, if I just rearrange these terms, I can put it as y cap equal to beta naught plus beta 1 into x. Same thing that we were looking at, okay. Now, when I'm talking about y cap, I'm talking about the predicted value, okay. So with the predicted value, there can be certain error associated, right? The prediction can be closer, okay. So the prediction can be exact, The prediction can be a little bit above what is the actual value, or it can also be a little bit below than the actual value, right? So to adjust that, we need to add the epsilon parameter or the error term over here. Okay. So let us talk about this. If the expected output was 50, okay, y is 50, okay, actual value is 50. My regression equation predicted y cap is nothing but the predicted value. If it predicted as 55, now is it different than the actual or expected value? Yes. Then we find out the error as error is nothing but actual value minus the predicted value. So what is the actual value? Actual value was 50. Predicted value is 55. So the error becomes -5. Okay, so this is your epsilon parameter E. All right. So now we understand what is the error. Okay. And now we will revisit our concept of best fit line. We are trying to figure out what should be the best fit line out of all these different lines that we have drawn, right? The blue line, red line, green line, violet line, or the yellow line. Which line to choose as the best fit line? Why? Why are we interested to find the best fit line? Because that best fit line should be the representative of all the underlying data points. Do you guys agree with me? How do we choose your representative in elections? You need a person who is a representative of the all the sections of the society, right? Poor people, rich people, all the middle class people, right? If you should not choose a leader who is biased to a certain section of the society, right? You need a representative who can cater to all, right? So similarly, you want a line which is representative of all the underlying data points and not inclined or biased to a specific set of data points. Okay. So we need to find out such a line which is the best representative of all the underlying data points. Correct, Rohit. We go by the voting mechanism. Now, so basically, if we apply the same logic, we are interested to find a line which is generating minimal error. And how do we find out that? So in terms of regression equation, okay, so I'm just going to the next slide now. So let us pick one line. Sorry. So let us pick this line, okay? And as we talked about, right, this line is nothing but y cap equal to beta naught plus beta 1x plus your epsilon, okay? Now, what is this? The slope is nothing but this. This is the slope. Slope is nothing but represented by your beta 1, okay? And wherever this line intercepts your y-axis, so this is nothing but your beta naught, or also called as your C, okay? Now the terminology is clear, everyone? Beta naught, what is beta naught, what is beta 1, right? Those are nothing but your replacements for M and C, okay? With me so far? Now, if we have chosen one line, okay, so whichever I explained on the last slide, Rohit, do you remember why the error term? I am generating a prediction. The prediction can be close to the actual value. It can be more than that, or it can be less than that as well. Correct? In order to find out, okay, how much I am deviating from the actual value, I need to define the error term. Error is nothing but actual minus predicted. Okay, let's come back. Now I have chosen a line. Okay, let's say I have chosen a line L1. Okay, I'm going to find out whether line L1 can be the best fit line. Okay, so what I'm going to do now is, okay, so whichever point you pick on this line, okay, this is your y cap, predicted value. Okay, so when your years of experience is 4, okay, the predicted value will be somewhere over here. So this is on the line. Okay, this is on the line. So this is your y cap, guys. Okay, predicted value. But the actual value is over here, right? So this actual dot is your y. And the difference between your y and y cap is what? Error, right? Actual minus predicted. Yes or no? Everyone with me? So the difference between your line, the point on the line, and your actual dot is nothing but this distance is nothing but your error, guys. Okay, so this is the error. So if you draw a perpendicular line, okay, to the line, so these are all your errors. Okay, so I'm going to choose a line which will result in minimal errors, which means that all the data points should be as close to the line as possible. Okay, and in order to find out such line, I'm going to use the ordinary least square method, OLS method, as it is called as. Now, what is this OLS method or ordinary least square method? This method says that, okay, go with that particular line. So I have chosen L1 over here. Maybe I can draw another line over here, which is L2. Okay. So how will I determine whether L1 is best or L2 is best? Basically, I'm going to apply the OLS method or the ordinary least square method. So what is the ordinary least square method? For every data point, I'm going to calculate the error. Okay, this is the error, this is the error, right? So this is the error, so this is the error, right? So E1, E2, E3. So whatever, if I have 10 data points, right? 10 data points, I'll have E1, comma E2, comma E3 up to E10. Okay. What I'm going to do is, what OLS says that the sum of the summation of, okay, the line which gives me the least sum of squared errors, okay, the line which gives least sum of squared errors. Okay, now I am saying this. Okay, so this is your E1, E2, this is E3, this is E4. Now see, whenever error can be positive as well as negative. If you check the error in the last slide, we got -5. Similarly, we can get error in positive terms as well, right? But if I square them, right? If I square them, this will be 25. This will also be 25, right? So it doesn't matter. So if the point is above the line or below the line, okay, since we are squaring the terms, right? It doesn't matter. Okay. End of the day, we are going to have a positive value. Okay. So likewise, this is, let us say, for E1, this is for E2, E3. Likewise, I'm going to take all the E10, all the 10 errors, okay, square them up and take a summation of all of them. Okay, sum them, all of them. So I'll sum of all of these, okay, squared errors. So the line which is going to give me the least sum of squared errors, this value, whichever line gives me the least value for this, is going to be my best fit line. Is this point clear to all of you guys? How do we choose our best fit line? How do we finalize out of the infinite lines that we can draw, okay, representing the points? How do we choose our best fit line? Are you getting this? Shouldn't the line be? No, Rohit, it need not pass through the origin always. See, there are two scenarios in which your y-intercept can be on the positive side. Okay, so this y-intercept, here you are on the positive y-axis. Okay, but there can be cases when the line will pass below also. So in this case, this will be your minus y, negative value. So in that case, your intercept will be negative. In this case, your beta naught. Okay, here in this case, beta naught is negative. In this case, your beta naught will be positive. So it need not pass through the origin. Okay, it can go above the origin or below the origin as well. All right. Are we clear, guys? Is this concept clear? How do we choose our best fit line? Yes, no. Is the concept clear, everyone? Okay, great, Rohit. Great, Gangotri. All right, now that you guys have understood the best fit line, okay, now we are going to look at our best fit line. Okay, let's understand this with a business use case. Okay, so let us say I have a newspaper data, okay, from all the leading newspapers in a metropolitan area. Okay, now all these newspapers, there are 34 newspapers. Okay, they have their daily edition, okay, as well as they have their Sunday edition. Okay, so what is the daily edition? So daily edition is nothing but it runs from Monday to Saturday, and on Sunday they run a special edition. Okay, so which is called as a Sunday edition. So a new newspaper, okay, has come into the market, which is running currently on a daily basis. Now they're trying to start, they're thinking, okay, they're trying to figure out what is the feasibility of starting a Sunday edition. Okay. Now, in order to start a Sunday edition, they're going to look at the past data of 34 different newspaper, like what is their daily and what is their Sunday sales. Okay. Now, depending upon the analysis of daily to Sunday, they are going to determine whether they should start a Sunday edition or not. Okay. So now tell me which is the dependent variable over here and which is the independent variable over here. Sunday is dependent. Yes, Gangotri. Yes, Rohit, you guys are right. So Sunday is the dependent variable. Now, how would my equation look like? Remember our equation? What was the equation? Predicted value y cap is equal to beta naught plus beta 1 into x, right? So plus epsilon. Now, what is y cap? What is x over here? Can anyone tell me? What are we trying to predict? Sunday sales, right? So Sunday cap is equal to beta naught plus beta 1 into your x is nothing, input is what? Nothing but your daily sales, right? So this is your regression equation. Okay. And you have your daily data, you have your past Sunday data. The only unknown parameters are your beta naught and beta 1, which you can learn. Okay. So the parameters beta naught and beta 1 will be learned from the data. Just as similar to years of experience and salary, right? We plotted the scatter plot, and from that we determined the best fit line. Once you get a best fit line, so I'm going to take these data points, okay, plot them, okay, find out the best fit line which runs through all of those. Once you get a best fit line, how do I find the best fit line? The line which gives me the least sum of squared errors is going to be my best fit line. Let us say this is my best fit line. Okay, so this will have certain equation y cap equal to beta naught plus beta 1 into x, where beta naught is nothing but this y-intercept, and there is a slope associated with this line as well. So once I get my best fit line, I can find the slope of that line and the y-intercept. Okay, plug in into this equation, and then I'll get a regression model. Then what you need to do? Just for any given value of x, plug into this data. You have learned these values from the data set. So you have these certain values, multiply with x, solve this equation, get your y cap or predicted value. As simple as that. Everyone? Okay, let's do this step by step. So tell me, how do we find out whether these two variables are related to each other or not? So I'm going to plot the daily circulation as well as the Sunday circulation. Do you see some sort of relationship between these two variables? Daily sales and Sunday sales? Directly proportional, yes. Positive relationship, yes. So if you see this, I can run a line through this, okay? And as you can see, this is a positive correlation. There is a positive correlation. So as daily circulation increases, your Sunday circulation also increases, right? So there is a positive relationship between these two variables. Okay, now tell me which line to go for. Let us see if you guys have understood the concept of best fit line. So which one? The one which is having a red border or the second plot I should go with? So by visually looking at it, Rohit, tell me which will have a less OLS. Which line do you think is the best fit line out of these two? The one with the red border or the one which does not have a border? Okay, so majority of you guys are saying the one with red border. But why? You need to support your answer with the reason. Yes, Chandrika, why red one? What is the logic behind choosing the first plot for best fit line? Yes, Khushi, error is less. Okay. It's close to the maximum data points touching. Okay, all right. All right, great. Correct, Rohit. The errors getting generated in the second plot are more. If you see, this is your actual y point, and the one on the line will be your y cap, right? So if you see, this is a huge error. This error is pretty huge, right? Whereas you can see these are all small errors, right? So this is the best representative of the underlying data points. All right, good. You guys have understood the concept. I'm glad. Let's continue. Okay. So this is what your equation would be. So we are interested in predicting the Sunday sales. Okay. Beta naught plus beta 1 into daily plus your epsilon. Okay. Now you can also figure out the beta naught and beta 1 using this concept of mean. Okay. So your y bar is nothing but the mean of y values. X bar is nothing but the mean of x values. Okay. So if you plug into this equation, you can also get your beta naught slope and your beta naught, which is your y-intercept. Okay. So once you get the slope, you need to plug in into this equation in order to get your beta naught. All right. Okay, so in Python, we have different libraries which will do this for us. So anyways, I'm going to show you the practical implementation as well. Okay. Okay, so now that we have found our best fit line, the best fit line equation or the regression equation is y cap equal to beta naught plus beta 1 into x plus epsilon. Okay, we will learn the beta naught and beta 1 from the data set. Okay, x we already have it, and y cap is something that we are interested to predict. Okay, now this is once the model is built, we are trying to understand how good is this model from prediction point of view. Okay, so in order to understand the goodness of our model or how good our model is, we go with something called as the coefficient of determination, which is also called as the R square value. Okay, you'll always hear about this term, something called as R square value. Now R square value is nothing but, okay, the proportion of variation in y or your target variable explained by regression on the input variable, which is the x variable. Okay, so by doing regression on x or regressing on the input variable, how much proportion of variation in y is this x variable able to explain? Okay, so that is what your R square indicates, and the higher the R square value, the better the model is. Okay, so R square value always lies between 0 to 1. Okay, if the value is closer to 1, it indicates a good fit. If the value is closer to 0, it does not indicate a good fit. Okay, so basically, whenever your R square value is not closer to 1, so let us say if I have R square value which is almost like 0.80, do you think is this a good model or is this a bad model? It's a good model, right? Correct. Very good. So if I have R square value, let us say, if I have, let us say, R square value, which is almost 0.61. What do you think? How is the model? Just above average? So if I consider 50% as the average, or is it a good model? 60? Moderate, average. It is just above average, right? Not the best model or not a very good model, right? So the R square value also tells that x alone is not able to explain the complete variation in y, and that is the reason it is getting a lower score. Which means that x alone, when I say x alone, in this particular example that we are talking about, right? X is what? Your daily sales. Daily sales. Okay. And your y was your Sunday sales. Okay. So this means that if I get a R square value which is very low or just above average like this, okay, it means that x alone, this one variable alone, is not able to explain the total variation in y, which means that there are some other factors also which are contributing in determining the value of y. Okay, so in that case, okay, so this is the equation of simple linear regression. Okay, SLR. In simple linear regression, we just have one input variable and we just have one output variable. Okay, So when you have just only one input variable and one output variable, that is when we call it as a simple linear regression. Okay. But if you're getting R square value, which is very low or almost above average, okay, it means that X alone, this variable alone is not able to explain the variation in Y. Basically, Y does not derive its value only from this X variable. Maybe this is just X1. Maybe there is X2, there is X3, X4. There are more features as well. Okay. So the Y variable is deriving its value from multiple variables. Okay. In which case we cannot work with SLR. We need to go with something called as MLR, which is nothing but your multiple linear regression, wherein you will have multiple input variables such as X1, X2, X3, and so on up to Xn. Okay. And one target variable. Is the concept clear, guys? When do we say it is SLR and when do we say it is MLR? When do we say it is simple linear regression and when it is multiple linear regression, right? Very simple definition, right? Okay, so Rohit is asking, sir, tell about SSR and SST. Okay, so here you go, SSR and SST. So this is how you derive your SST, total sum of squares, okay? And then you can also derive your SSR, which is nothing but regression sum of squared, okay? You can again apply this formula. Now for this, you need to understand what is your degrees of freedom, okay? So I would suggest you to go through a book called as Complete Business Statistics, okay? So this will, help you to understand majority of the statistical concepts, okay, which are required for you to understand this mathematical terms in detail, okay. But if you ask me, do we really need to bother about all of these? No, you need not by heart these equations, or we do not derive these equations. You don't have to plug in the values and arrive at a value, okay. Today we have Python libraries which can generate this output for you. For us, it is more imperative to understand, okay, how we can build a model, how we can solve a business problem using all these tools available at our hand. Okay. All right, Rohit, does that answer your question? All right, guys, let's move on now that you guys are clear. Okay, so we'll look at this Python implementation at the end of the session. So let us move on. So this is what the output will look like for the daily newspaper and Sunday newspaper. Okay. But let's move on to MLR quickly. How are we doing on time? 8:24. Okay. So let us look at multiple linear regression, and altogether we will look at the Python example, which I will show you how to implement SLR and MLR in Python. All right. Shall we proceed to MLR now? Guys. Okay, cool. Let's move on. So we already talked about when in which cases we would need to go for MLR. So when one variable alone is not able to explain the variation in Y, or you can say that Y does not determine Y. What is Y? Y is a dependent variable, right? Like in case of salary and years of experience, right? So Y is the dependent variable, okay, which means that it is dependent on someone to derive its value, right? That someone is nothing but your input variable X. So when one variable itself is not able to explain the total variation in Y, which means that Y does not derive its value only from X1, but it also takes contribution from X2, it also takes contribution from X3, and so on, right? When we have multiple input variables involved, okay, because of which through all of them Y is able to determine its value, okay, that is when we are going to say that we are going with multiple linear regression, or we are solving a MLR problem. With me, guys, so far? We talked about why multiple linear regression and so on. Okay. So I can give you one more example as well. Okay. So on this carvalet.com, let me show you that. Okay. So cars24, carvalet.com, right? These are the platforms where you can sell your car or buy a used car and so on, right? So let us say we have a used car. Okay, I am the first hand owner of it. Okay, if I am planning to sell that car, okay, I want to understand what is the value of the used car that I should expect. Okay. So what is this website asking me? This website is asking me, okay, what is the year? So when was the car manufactured? Let us say 2015. Let us say my current city is Pune. Let us say the car that I own. So majorly Maruti is the one which sells most cars in India. So let us take Swift Desire, right? Very much popular model. Let us take the diesel model. Okay. So I'm the first owner of this. Okay. So let us say the kilometer driven is 50,000 kilometers. Okay. So now it is saying me, okay, check the value. So if I click on check the value, now it is telling me that, okay, you can expect the car to be sold between 4.8 lakhs to 5.3 lakhs. Okay. So in this case, what is the output variable, guys, or the target variable? The target variable is nothing but your price of the car that you can expect, right? So this is your prediction of the price. Okay. So you can, there's a price which has been predicted is between 4.8 to 5.3 lakhs. Now, again, why I'm getting a range? Because depending upon the condition of the vehicle, you can either expect 5.3 lakhs, or if the condition is not very good, you can almost expect around 4.8 lakhs as well. You can also have more if you have a music system, you have leather seat cover, blah blah blah, all are in good condition. You can also expect some more around 5.3. You can expect 5.4 as well. Okay. But how is the website coming to this conclusion of this price range? Okay. It is coming based on the values that we gave it to it. Okay. So basically, let's say evaluate again. Okay. So if you see here, price is nothing but dependent upon, so the price of the car that you can expect is dependent upon what? So this is beta naught, okay, plus beta 1 into what is the first thing? Year of manufacture. So year plus beta 2 into what is the second? City. In which city are you using it? So this is the second variable, plus beta 3 into the car, the make or the model of the car, right? So it was Desire that we selected, plus beta 4 into whether you are the first owner, second owner, or third owner, right? So whenever you are the first owner, basically you can expect a good price, right? When it is again sold to the second owner, maybe if you're already buying a second-hand used car, you might expect still less price for it, right? So this is also an important factor. So let us say the owner, whether you're first, second, or third, that also plays an important role. Then beta 5 into, then what is the kilometers driven? Yes, obviously how much you have used the car, right? So based on that, this is how your multiple linear regression equation that is running behind this website, which calculates your used car price, guys. So this is your multiple linear regression equation. Are we getting this, guys? So yes, Rohit, for that you need to understand the statistical concept of something called as confidence intervals. Okay. So at 95% confidence, what is the range I can expect? If I say at 90%, what is the range I can expect, right? So based on the confidence intervals, right, you can get a range of values as opposed to a exact price. I'll show you when we do the uh, what you can say implementation in Python. I'll show you how that confidence interval is plotted on the graph. Okay. But so far, is the concept very clear? Again, I'm showing you a practical example of how it is being used in day-to-day business. Very much relevant. Are we able to sense how this is being used in practice? Yes? Everyone understands now? Cool. So let's clear off the slide. And then we will go to the slides. Okay, so this is your equation of MLR. Okay, so you can expect beta naught plus beta 1 x1 x2 up to k number of variables plus epsilon. So this is nothing but your beta 1 into your year, your city, right? Similar thing that we saw for our Carvalho or Car 24, right? So same thing how they use it. So instead of the original equation in SLR, which was y cap equal to beta naught plus beta 1, okay, x, that we need to just expand for multiple variables. So when we have multiple variables, we have the coefficients also associated with them that will be accompanied with those. Okay. So this is how your MLR equation looks like. Now, when we work with this MLR equation, guys, there are certain assumptions that we need to assume or, go by. So here we are assuming that all the parameters are linearly associated. So basically the linearity is assumed. Okay. Now, about the errors that are being generated, right? So those should be identically and independently and identically distributed. Okay. Basically, they should be normally distributed. And when you take the mean of all such values, it should come to 0. Okay. The errors basically. Okay. It should have constant variance, which is homoscedasticity. All the error values are, basically independent of each other. They are not dependent on each other. Okay. Now this is about the predictors. Predictors are nothing but your x variables or the input variables. Okay. Those are all non-random. Okay. So they have been measured with utmost care. Okay. There is no errors associated when the values are captured. So that is what measured without error. They are linearly independent of each other. So basically your x1 and x2 and so on, whatever number of n number of variables that you have, they should not be associated with each other linearly. There should be no linear association between each other, or they will face a problem called as multicollinearity. Okay. So this is something that you can look up on the web if you want to learn more about multicollinearity. Okay. We won't be able to cover up in this session today. Okay. But yes, all the assumptions about the observations. So basically all the data points that you have gathered in the data set, they are all reliable data. It is not hypothetical data, but a real data. Okay. So that is what is the assumption over here. Beta, which beta? Beta 1, beta 2. Yes, betas can be 0, Kushi. For multiple, how we will select the best fit line? It is, you have to imagine a multidimensional space, Rohit. Okay. All right. Any new messages? All right. Good. Let's move on. Okay. So we are going to work with a cast data set wherein we have these variables. Okay. So there are total 81 observations. There is volume. Let us say this is X1. HP, let us say this is X2. Okay. SP weight. Okay. These are nothing but X3 and X4. And this miles per gallon or also the mileage of the car. Okay. So the mileage of the car is nothing but dependent on the volume of the car, the horsepower of the car, the top speed, and the weight of the vehicle. So this becomes your Y or the target variable. So our interest is to model the MPG of the car based on the other input variables. Okay. So your equation will look something like this. Miles per gallon predicted, regressed on. So this tilde is nothing but regressed on. Regressed on HP plus SP plus weight plus volume. Okay. And in terms of regression equation, if I have to say, this is nothing but y cap equal to beta naught plus beta 1 HP plus beta 2 SP plus beta 3 weight plus beta 4 volume. This is into, okay, plus epsilon. Is this clear, guys? Everyone? With me so far? Yes, no? Okay, great. So now let us look at if we run MLR on this particular data set, how will it look like? First, we need to find the relationship between the variables. Remember, in case of simple linear regression, we plot a scatter plot and we look at the relationship. Now, if you look at this particular scatter plot matrix, since we have multiple variables, we are plotting a scatter plot matrix. Okay. Now, if you look at the relationship between HP and your miles per gallon, what kind of a relationship do you see? So this is your input variable X1 and this is your output variable. So what kind of a relationship do you see between these two? If you see the intersection of both this line and column, right? This is the graph which represents the scatter plot. What kind of a relationship is there between HP and MPG? Can anyone tell me? Is your mileage affected by the engine horsepower? Yes, negative relationship, right? As you can see over here. There is negative relationship. So if the horsepower of the engine keeps on increasing, your mileage will go on decreasing. To give you a very simple example, if you own a Royal Enfield of 350cc, and if you put 1 liter of petrol in it, imagine how long it will go as opposed to, let us say, Bajaj Discover, which is 100cc bike. Which one will give you more mileage? Royal Enfield with 350cc will give you more mileage on 1 liter of petrol, or 100cc Bajaj Discover will give you more mileage on 1 liter of petrol? What do you think? Obviously, 100cc engine Bajaj Discover will give you more mileage, right? So as your engine capacity goes on increasing, right, it will consume more fuel, right? And that is why there is a negative relationship between your HP and MPG. I hope that is clear, everyone. You should be able to understand what kind of a relationship exists between each of these variables. All right. Okay, let's move ahead. Now, this is the output of your regression. Then when you run on this particular variables, okay. And how do we validate this model now? So in order to validate MLR equations or MLR model, we need to understand or study the residuals. Residuals is nothing but a different name for the error. Okay. So let me first tell you what this thing is all about. Do we have an empty slide? No. Okay, hold on. Let me insert a slide over here. I thought there was one. Okay, let's go full screen. Okay. So first, let's try to understand why it is important to understand or study the errors or residuals. Okay. So let us say if this is your data. Okay. Let us say if this is the model. Okay. And this is nothing but the residuals, or you can also call them as errors. Okay. Now, let us say the data was something like this. Okay. Bear with my. So let us say if the data is something like a sine wave. Okay. Now, this is the pattern. The sine wave is the pattern in the data. Okay. Let us say when you train the model, let us say if the model is able to capture this pattern. Okay. The model is able to capture this particular pattern of the sine wave. Okay. So when the model is able to successfully capture the patterns from the data, okay, there will be nothing in the errors. The errors, okay, when you plot the error data points, okay, there will be no relationship or there will be no patterns that you will be finding in the errors or the residuals. Okay, when you plot the error data points, there will be no patterns, okay, or will be randomly distributed like this. Okay, but let us say if there is a different pattern, okay, there is a complex pattern in the data. Let us say this pattern is something like this, like plus 5 volt to minus 5 volt. Okay, so this is something like this. Just for example purpose. Okay, let us say this is a pattern, and when you train the model on this kind of a data, the model is not able to capture this pattern. It's not able to capture the pattern because of its complexity. Then these patterns will leak. These patterns will leak into the errors. So since the model has not captured the patterns, these errors will get leaked into the these patterns will get leaked into errors. So if your errors or residuals are showing patterns, okay, if your errors or residuals are showing patterns, it means that the model has not successfully captured the pattern. Okay. So if your model would have successfully captured the pattern, there will be nothing that will be leaked into the errors. Okay. The errors will contain no information, no patterns, no patterns. Okay. But if the model is not able to capture the pattern, not able to capture, okay, then the patterns will get leaked into the errors. And that is the reason it is imperative or important to study the residuals or the errors. Is the logic clear, everyone? Why we need to analyze or study the errors? Okay, cool. Great. So now let us look at these errors, okay, and their analysis. So when we analyze the errors, okay, we analyze the errors versus the yi cap plot. So what is that particular? So errors is nothing but the error data points. So ei nothing but e1, e2, e3, and so on. So if I have 10 data points, okay, so I will have y1, y2 up to y10. Similarly, when I do the predictions, y1 cap, y2 cap, and so on up to y10 cap, right? So difference between the actual and predictor will nothing but the errors, okay? So this will be e1 to e10, okay? And these errors I can plot on the scatter plot, okay? So I'm going to plot a scatter plot between ei versus yi cap. Now, what is this yi cap? Yi cap is nothing but these predicted data points. So this predicted data points versus the error data points is what I'm going to plot as a scatter plot. So this is nothing but ei versus your yi, okay? So ei versus your yi, okay? And now what is the expected thing over here when I plot error versus your yi? So it will be used to check for linear relationship, okay, constant variance. And then you need, if you basically what, when you plot the data points right over here, like in the scatter plot, there should be no patterns. As I said just now, right? If you see patterns in this particular, this kind of plots, it means that the model has not captured the pattern and the pattern has got leaked into the errors, okay? So you can plot this. You can also plot something called as errors versus your xi. Xi is nothing but all your regressor variables like x1, x2, x3, x4, and so on. Whatever number of xn number of variables that you have, you can plot the data error versus all the individual variables and see if there is some pattern that is emerging out of those plots. Okay, if there is no pattern, which means that the model has successfully captured the pattern in the data. Okay, and the last plot is something called as the QQ plot, which is also called as the quantile plot. Now again, this is just to check if the error data points, EI data points, are normally distributed or not. Now, the other way to check normal distribution is to plot a histogram as well. So if you plot a histogram or if you plot a distribution plot, you can also see that if there is a shape like this, which is of the normal distribution, okay. If all the error data points show a normal distribution, okay, that is also a way to check whether your errors are normally distributed or not. Or you can also plot something called as a quantile plot. Then how do we interpret this quantile plot? So let us check all of those. So this is nothing but your fitted values, nothing but your yi cap, okay, and your residual values is nothing but your ei, okay. So this is the first plot, ei versus yi, okay. So if you see that these are all randomly scattered points, right? There is no pattern in this. So when there are no pattern, there are no problems. So the model is good as it has captured the patterns, and the mean of all the errors should be equal to 0, which means what? Your EM, E1, E2, E3, E4 up to all E10 data points, right? If I take summation of all of them, okay, if I sum all of them, this should be 0. Okay, so that is what your, so sum in the sense divided by the number of data points, which is 10. So this is the mean, actually, average. If I take the average or mean, it should be 0. Okay, so this is the first plot. Now this is the QQ plot or the quantile plot. How do we interpret this? So if you look at this thick line, right? Thick line, red line. So this thick red line is nothing but around which all the data points. So these are all your error data points. Okay, these are not normal data points. These circles that you see, right? These are error data points like E1, E2, E3, right? Up to whatever number of data points we have. So we have almost 77 data points in this cars data set. Okay, so all these data points, okay, should be on this solid red line, which indicates that they are normally distributed. Okay, they are normally distributed. If they are not on this thick line, they should be at least in between these dotted lines. Dotted lines kya hai? This dotted lines is nothing but your 95% confidence interval that I talked about, right? So this is the 95% confidence interval or 95% CI. So the error point should at least lie within 95% of CI, okay? Which means that still we can consider them as normally distributed, okay? If majority of the data points are outside this 95% confidence interval, okay, so they are neither on the thick line, neither on this in between these dotted lines. If they are outside like this, okay, which means that these data points are not a part of this distribution. Again, majority of the data points are within 95%. Here we can see these are normally distributed. But if the majority of the data points are not on this line or within this dotted lines, we can say they are not normally distributed. There is some pattern that you can expect in those errors or residuals. Okay. So this is the second plot we talked about. This is the last plot, residual plots. Okay. Regressors versus residuals. Regressors is nothing but xi versus your residuals is nothing but your ei. Okay. So against each, since we are having four different variables or input variables in this particular example that we're looking at. So for every variable, okay, for every xi, okay, we will be generating these four different plots. Now, what are these four different plots? Four different plots are nothing but your blue dot is nothing but the MPG or the target variable y, okay, and we want to see how much volume is contributing in generating errors in your MPG, okay. So if you look at this particular lines, okay, so this blue dot is your actual, your orange dot is a predicted one. So if there is difference between these two, predicted and actual, which means that there is error which is being introduced because of this volume variable. Okay. And if you look at this CCPR, again, this is residual versus volume. What you can expect here, there should be no patterns over here. And if you want to understand whether volume, okay, so this is the volume is really contributing in determining your miles per gallon. Okay. Is there some relationship between them? So for that, we need to look at this partial regression plot. Now, partial regression plot, what to look for? If you look at this line, this should have certain slope. But if you're not able to determine that whether there is slope or not over here, okay, which is very thin slope over here, right? So you should refer to the CCPR, component and component plus residual plot, which is also called as a CCPR plot, which will clearly indicate the slope for you. Okay. And as you can see, there is a good amount of slope over here, which means that volume is highly contributing in determining the value of your target variable, which is your miles per gallon. Okay. So this is how we can interpret, okay, whether those input variables are related to the target variable or not, okay, whether they're contributing or not. Can we visualize? Yes, Rohit, we can visualize all these plots. Okay. There are Python libraries with which you can visualize all these plots. Okay. So that's all, guys, with MLR, SLR and MLR. Okay. So I'll quickly go over a Python code to show you how this can be implemented. Okay. Again, that is basic Python code, which I'm going to showcase using Jupyter Notebook. Okay. So you can install Anaconda as the, what you can say, IDE, okay, the integrated development environment. So Anaconda is just like an IDE, okay. So you can use Anaconda, you can use Spider, okay. There are a lot of IDEs available, okay. These are nothing but Jupyter is usual. Jupyter notebooks are easy to comprehend, okay. So you can immediately run one single line of code, see the output, and then you can go to the next ones, okay. And that is the reason we prefer Jupyter notebooks to showcase something when we are in the learning phase. Okay. But in production, we don't implement Jupyter notebooks, we implement the Python scripts. Okay. Master data science. All right. Is the screen visible to everyone? Guys? Is the notebook visible to all of you? Yes, no. Okay, great. So I assume majority of them are engineering graduates or students, right? So you might be familiar with Python. If not, I urge you to use a book called as Learn Python the Hard Way. Okay. Or there are multiple tutorials available on YouTube. There are multiple like W3 schools and there are a lot of websites which are offering you all these things. But if you want to learn through a book, this is a book that you can follow in order to learn Python. Okay, step by step you can learn Python. So for people who are not coming from the computer science or your IT background, right? You guys can refer this book in order to learn Python. Okay. All right. That said, let's start. So we're going to use few of the libraries which are important from the data science perspective, which is pandas. Okay, pandas works you to help. Helps you to work with Excel-like structure. Okay, so basically your data sets. are majorly into ExcelR structure. So we are going to work with pandas that will help us to crunch that data set. Matplot is useful for visualization. Seaborn is also advanced library for using generating attractive visualizations. Okay. Now stat models dot graphics dot regression plot, that we are going to use this basically for generating the plots. Okay. Stat models dot formula API again to run the regression models. Okay. We are going to use the statistical libraries. NumPy is nothing but numerical Python, which is if you want to find square root, square, these kind of operations you want to do, mathematical operations, you can find those functions defined in these particular libraries. All right. Okay, so that was just an introduction to this libraries, Python libraries. I'm going to run this. I have this data set, which is cars data set. We just now discussed about cars. So we have horsepower, volume, SP, weight. These are the 4 different variables that we have. Okay, so you can think of these as your X1, X2, X3, right? X1, X2, X3, and X4 variables. And this is your target variable or the Y variable. Okay. So first I'm going to show you one input variable and one output variable, okay, which is nothing but how you run your simple linear regression. Okay. So you can generally do cars, data frame.info to see, how many non-null values you have, what is the data type of this, okay. These are the column names, okay, and so on. Okay, are there any missing values? No, we have the entire full data set. Okay. You can check the correlation. Okay, so this is the correlation matrix. You can see, okay, diagonally, how do we interpret this output? So you look at diagonally, all the values will be 1, which indicates that the correlation with self will always be 1. So MPG with MPG will always be 1, volume with volume will always be 1, right? So correlation with self will always be 1. So that is the reason you need to ignore the diagonal values. How we can find out what is the correlation between HP and MPG? So you have to look at the intersection of row and column, and this is the value for that. A negative value indicates that HP and MPG are negatively correlated. You saw that in the graph as well, right? So the data points were something like this. So there was a negative correlation between MPG and HP, if you guys remember, right? Okay. Then let us see how we can run a simple linear regression model or ExcelR model. Okay. So for that, we are going to look at SMF. SMF is nothing but the stat models formula API. Okay. So we are going to generate aliases. Okay. So for pandas, instead of writing the entire pandas, we just use the alias name, which is PD. So in order to invoke functions from the pandas library, we are going to say PD dot something, PD dot read CSV like this. So PD dot read CSV. This invokes a function from pandas in order to read this file, input file. Okay. So similarly, SMF is coming from your stat models formula API library. So in order to invoke the function from that, I'm going to use alias dot smf dot OLS method, ordinary least square method. Okay. MPG is nothing but the target variable Y. Okay. So Y regressed on. So Y regressed on the input variable X. Okay. So since we are talking about simple linear regression, only one input variable and one output variable involved. So MPG regressed on volume is what we are looking at. Data is equal to data set or your data frame, which is cars. Okay. Dot fit will fit the data such that we will find the best fit line. Okay. All right. So you can use the SNS dot regression plot. Okay. And plot this. Let me first run this. So you can plot this kind of a regression line. Okay. Now this dotted portion is what is your 95% confidence interval, guys. This dotted shaded portion is nothing but your 95% confidence interval. I think someone was asking it during the session. All right. Okay. So we can do it on HP as well, where there was negative correlation, right? So let us see what is the regression plot look like. So this is a regression plot, guys. So this is the best fit line, which is representative of the underlying data points. And this is the 95% confidence interval. So someone asked, right, how do we predict the range of values for the used cars, right? So this is how it predicts the range of values for that particular best fit line. All right. Okay, coming to MLR. Okay, this is the R squared values. Let us look at the R squared values. So the R square is 0.52, which means that HP alone is not able to explain the variation in MPG, which is nothing but MPG does not only derive its value from your HP, it is also dependent on other variables, right? Which means that we need to go for multiple linear regression. Okay. Now, what is this adjusted R square? Adjusted R square is nothing but if addition or deletion of a variable, okay, if addition or deletion of a variable, okay, due to the addition or deletion of a variable, whether there was change in the performance of the equation, regression equation or not. So whether you added if you add an unwanted variable into the equation, the performance, this R square will go down, adjusted R square will go down, indicates that you have added a unimportant variable or an not required variable, which is not contributing to a target variable. Okay. But if you add a useful feature or a useful variable, which is helping us determine the value of our target variable, MPG, in that case, the adjusted R square will shoot up, indicating that you have added a useful variable to the equation. That is the use of your adjusted R square. Okay. All right, coming to the multiple linear regression. Okay, so here we are going to run regression on multiple variables. As you can see over here, MPG regression on volume plus HP plus SP. Data is equal to cars. I'm going to fit the values. Okay, so let us see what is R square. Now, as you can see, right, earlier when we ran with only one single variable HP, the R square value was 52.52, which was almost average model. Now, what do you see, guys? Has the performance bumped up? What is R square value now? Has the R square value gone up? Yes, it has gone up, right? Which means that the performance of our model has improved because of addition of multiple other variables which are contributing in determining the value of MPG. Okay. So this is how you build a multiple linear regression, guys. Okay. Now, once your model is ready, how do we use it for prediction purpose? So what you need to do is you need to take a new set of input values. So I'm going to just take the new set of input values. Okay. And I'm going to, so if you see here, we had created the instance of the model ML underscore WV. So on this ML underscore WV, I'm going to use the dot predict method. This dot predict method is used to generate predictions for the new data. So whenever you have new data coming in, okay, you can generate the predictions. So here, given a car which is having HP 40, volume 95, SP 102, and weight 35, what is the expected mileage of that particular car? So that is what my model will predict. So I'm going to pass this new data to the predict function. And as you can see, I can find out the prediction. So the MPG is nothing but 43.36 is what you can, is the mileage that you can expect for the car of this particular configuration, guys. Okay. So this is how we can build simple linear regression, multiple linear regressions, and use it for prediction purposes, guys. When you actually predict a value, we call it as a regression problem. Okay. When we are actually predicting a value, okay, a number, we are going to call it as a regression problem. Tomorrow, we are going to look at something called as classification problem, wherein we are not interested in predicting an actual value, but we are more interested in predicting to which class a particular data point might belong to or will fall into. Okay. All right, guys. So that's all from my side for today. Any questions that you have or doubts you have? A resource for regression. There are a lot of resources available out there in the internet, Rohit. You can just Google and find out. Okay. Kushi is saying thank you. All right. I hope the session was useful, guys. Yes. All right. Trisha is okay. Thank you. No worries. Any other doubts or queries you have? Okay, I think. Thank you, sir. All right. No problem. Gangotri. Rohit, it was a great session. Never thought of regression. I'm glad it helped you to clear your concepts, Rohit. Great. You're always welcome. All right, guys. There are no questions. If there are no questions or doubts or queries, okay. So I will conclude the session from my side for today. Tomorrow we will visit classification models. Okay. We'll understand what are classification problems, how to build classification models. Okay. We are not going to go the same usual model that is discussed everywhere. Tomorrow we will discuss an interesting algorithm to solve classification models, which is widely used. Okay. So stay tuned. We'll meet tomorrow. Okay. Until then, take care. And if you have any questions for Amar, Amar can take over.
Yeah, sure. Thank you so much. Guys, any question, please drop in chat box. We'll take it for 2-3 minutes, then we'll wind up for. So Chandrika's question is there, where we can get the recorded session. So Chandrika, please visit LMS. You will get the recorded sessions. Thank you for such wonderful sessions. Thank you, Sanjira. Sir, I missed my yesterday's session. How am I supposed to mark my attendance? So Shubnam, sorry. So Shubnam, we are not able to share the attendance link of yesterday because it's open between specified time of 8:30 to 9:30. So it's closed now. Don't, yeah, you will get the recorded session for that, but I'm not able to share the attendance link. Anyway, don't worry, 60% attendance is mandatory. So try to mark the attendance for remaining 2 days as well. I hope today you mark that. Yeah, for today you need to mark that. Yeah, I'm sharing the attendance link with you guys. Just a minute. Anything else? Attendance. Yes, guys, if you don't have any query or question, you can leave the session. We're done with the day. Roshan, what is the problem? Try to change the browser once. I'm sharing that with you personally. You're welcome, Kushi.